Okay, so this lesson is for chapter 4. And this one starts off with estimating roots, which you've done in the past, but now there's some new language associated with it. So the very first thing you need to take notes on is this. And so this is a radical as you've seen it before, basically a square root sign. But now we're going to be working with things that aren't just square roots, but they might be cubed roots, fourth roots, fifth roots, and things like that. So we call this little number out here the index. And so, for example, if I was doing a cubed root, the index of that would be 3. The index of a square root would be 2, even though it's not written. The thing underneath the little house is called the radicand. And then all of it together in a nice big bubble is called a radical. So you need to know that language because you might be asked things like what is the index, what is the radicand, and all of that kind of stuff. Okay, so the next thing you need to recognize is that square roots of perfect squares and cube roots of perfect cubes are going to be whole numbers. So basically what we're looking at is writing down over and over until you've got it drilled into your brain the first few perfect cubes and the first few perfect squares. So let's do that right now. So perfect squares, we're going to start out with 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, etc., all the way down. So these are numbers that if I took the square root of them, I would end up with a whole number. And you should know quite a few of them, at least up to 12 times 12, which is 144. Perfect cubes are the same idea, except now you've got numbers with whole number perfect or cubed roots. So basically I'm going 1 times 1 times 1 gives me 1, 2 times 2 times 2 gives me 8, 3 times 3 times 3 gives me 27, 4 times 4 times 4 gives me, let's see, what's 4 times 4 times 4? Of course, 64. 5 times 5 times 5 is 125, etc., etc. So now I'm looking at those and I'm seeing how am I going to use those when I'm simplifying radicals? And I'll get to that later. But the number one thing you need to do is be able to recognize these things really quickly so that when you're working on solutions, you know right off the bat what you're looking for. So 4.1 talks a little bit about estimating square roots and cubed roots and things like that. We can do a little bit of that. It's reviewed from last year, essentially. If I said something like estimate the root of, I don't know, 30, you know that's going to be in between the square root of 25 and in between the square root of 36. This is 5, this is 6. I'm going to estimate that it's about 5.5, maybe about 5.45 or something like that. We're going to use that same method for perfect cubes as well. So I'm going to find the perfect cubes around a certain number and then use that to guide my answer. If I was looking at, say, the cubed root of 8, however, well, I know that 8 is a perfect cube, so I'm going to just write the whole number representation of it right here. It also talks about rational and irrational numbers, and this is essentially all you need to know. That a rational number can be written as a fraction. So basically, it can be written as a fraction, which means if it's a decimal, it stops or repeats. And if it's irrational, it's basically anything else. So a decimal that never stops or repeats. So for example, pi would be irrational because it goes on forever, and as far as we know, in the millions of digits that we know of right now, it does not repeat. A rational number example would be 3, because it's 3.0 or 3 over 1. 1/2, 4.555 repeater. 3.15, 15, et cetera. Those are all rational numbers because decimal never stops for repeats. So that's really all you need to know. If it's asking you to take a cube root or square root of something, let's practice that and tell whether that's rational or irrational. So for example, it says, please tell whether, oh, I don't know, -3/5 is rational or irrational. Well, this is going to be rational because it's a fraction right off the bat. What about root 14? Well, I could just use my calculator, but I would know right off the bat, this is not a perfect square. Therefore, the answer is going to be a decimal one, and it's going to go on forever. So it's irrational. If I looked at the cubed root of 8/27, I could look at it as the cubed root of 8 over the cubed root of 27. And those are actually both perfect squares. That's 2, that's 3, so this would be rational. So it's just using those things that you already know in order to identify something as rational or irrational. So I'm going to leave that one. You can look a little bit more carefully through 4.2 to see which ones are like whole numbers, natural numbers, all that kind of stuff. What I do want to go through is 4.3. And this one actually is brand new. So it's talking about something called mixed radicals and entire radicals. So a mixed radical is something that is all underneath one radicand. So it's all underneath one radical sign. There's no big number out front. It might have a cube, or it might have a fourth here. It doesn't matter what the index is, but it can't have a big number out front. Oh, sorry, that's an entire radical. I lied. Ah! An entire radical has everything underneath the radical sign. I should do this instead. Okay, so an entire radical has everything under the radical sign, and then what I just said above for a mixed radical is that it should have a number out front and then the radical sign. Okay, so change that in your notes now that I messed you up. So basically we're going to be trying to switch in between mixed and entire radicals. So let's get right into it. So if I'm asked to please simplify a radical, that means I'm usually going to get an entire radical. And this is why, because it's all underneath the radical sign. And then I'm going to try and split it up into its pieces. So the first step when I'm trying to simplify something is to identify its factors. So I'm going to write out the factors of 80. I know 1 times 80, 2 times 40, 3 times nothing, 4 times 20, 5 times, what have we got here? Sorry, 5 times 16. Oh. Let me just fix this. So that works. Okay, 5 times 16. What else? We got 7, no, 8 times 10. Let's go with, I think that's it. Yeah, got everything else. Okay. So basically what I'm going to have to do now is out of its factors, find the largest perfect square factor. So find the largest perfect square factor. So if I look at all of these numbers, and this is why we really have to be quick with our perfect squares, if I look at all of these numbers, I'm looking for the largest perfect square that I can find. And that one right there, 16, is going to be our largest perfect square. So I'm going to split it up. just to note that I'm looking for the largest perfect square factors in this one. If I was trying to simplify a cubed root, I would look for the largest perfect cube factors. So for example, this one, let's split root 80 into root 16 times 5, because 5 times 16 equals 80. So I haven't actually changed it at all. And then I have a rule that tells me that I can actually split it up as a product of its factors. So that's what I'm going to do. So I've got root 16 times root 5. Well, root 16 happens to be a nice whole number. Root 5 does not, so I'm going to bring that one down to its nice whole number, write it out front, and then this is what's called simplified form. This is now a mixed radical, and I started out with an entire radical. So if I tried one more, something that looked like, oh, I don't know. Let's go with cubed root of 108. Well, I'm going to write out all of the factors of 108. And I'm going to actually look for all of the perfect cubes. So I'll let you write all of those down on your page. You'll get faster and faster at this as you go along. But I know right off the bat that 27 times 4 is actually going to be the one that contains the largest perfect cube. Why am I looking for the largest perfect cube instead of perfect square this time? Because it's a cubed root. Okay, so now I'm going to split this guy up into its two factors. Cubed root of 4 times 27 equals cubed root of 4 times the cubed root of 27. Cubed root of 4 is ugly, so I leave it. Cubed root of 27 is 3, so I'm going to write that nice and big out front. It actually doesn't really matter the order, but just be usually write the whole number right in front because it's multiplied. So again, I'm going to simplify this to a mixed radical. The last thing I'm going to show you is how to switch back from a mixed radical to an entire radical. So say I had something like 4 root 3. This is mixed, and I want to get everything all underneath one little house here, because that would be an entire radical. So that means whatever I did in the other one, which is split it up into its perfect squares, I want to do the opposite. So I know this number needs to be put back underneath the square root sign. So I'm going to do the opposite of square rooting it. So opposite of rooting it is squaring it. If it was the square, or if it was a perfect, sorry, if it was the cube root of it, the opposite of it would be cubing it. So now I'm going to square 4 and put it underneath the house. And that's 4 squared. And then I'm going to figure out what that is. So it's 16. And the 3 is still hanging out in there because I haven't lost it. And now I've got 16 times 3. Well, that's going to end up as 48. That's all underneath one house. So then I'm done. Okay, so that's up to 4.3. What I would like you to do is practice that quite a bit. This kind of stuff is going to end up in a lot of grade 10 math and a lot of grade 11 math. So you're going to need to know it quite well. Once you're done this, you can practice the exercises up to this point, and then you can hand in your assessment understanding on page 221 once you've practiced it all in each section. Okay, see you later.